So you'll remember last time I was working with the law of use of art. And if I'm not mistaken, I might have even got into Ampere's law. I'm pretty confident I got into Ampere's law. Let me check that just to make sure, though, because I hate to be confident about something I'm completely wrong about. But anyways, today we're going to finish off the chapter on sources of magnetic fields, and we're going to jump into the next chapter, which of course is electromagnetic induction and Faraday's law. So we're jumping into chapter 29 next. I want to make sure I'm covering all this. Okay. So yeah, it looks like the last time we were together, I did just the cylindrical wire using Ampere's law, as opposed to, of course, the law of use of art. And I was correct in assuming that. Okay, so that's good. Again, I'll ask one more time. Anybody have any questions before we get started on the new material, sort of new material, or some new examples at least? Okay, so here's what we're going to do. We are going to use Ampere's law now, since we've had our taste of the law of use of art. We're going to use Ampere's law now to do a little bit more robust problems. We didn't get a chance to do a solenoid or toroid last time. That's what we're going to do first. And I want to remind you guys that when we use the law of use of art, at least on arcs, and you're trying to find, say, the magnetic field, say at the center of the arc or the center of several arcs, then what we know is a magnetic field B equals mu0 times I over 2 times R. That is the magnetic field that exists at the center of a circle or a circular circle of wire carrying a current I whose radius is R. So it's mu0 I over 2R is that for a complete circle. So what that also means is if you have a half circle, then it's going to be half as much. Or if you double the radius, that too is going to make it half as much. If you triple the radius, it's going to make a third as much. If you cut the radius in half, it's going to make it twice as strong. So all sorts of stuff like that can be used. And then any lines that are radially pointing in, any current carrying wires that are pointing towards the center, can in fact be ignored, because basically the cross product of that is 0. So I just want to remind you about that. John Mitchell has a question, and actually I wish you would have asked us about a week ago, because I literally just discovered that I never posted test 3, even though I made it 2 weeks ago. So test 3 is now up, and what's going to happen is I think I made it due on the 19th. So this is due after excuse me, it's due after the midterm, but it's very much helpful for the midterm. So if you try to take that before the midterm, that would be helpful for you. It would not harm you. It would, in fact, help you prepare for the midterm. So that one's due not till the 19th, and probably what I'm going to do is make test 4. I'll either make that due on the 19th as well, or I'll make it the week after. But what's going to happen, because I completely just neglected to ever turn that test on, is we're probably going to have like 2 or 3 weeks where we'll have a test each week just to make up for that. And that's my fault. I apologize. I didn't mean to do that to you guys, but I really thought I had posted it. So I apologize on that. So anyways, back to the topic. Again, keep that law of use of art in mind. Mu0 I over parentheses 2 times R is the magnetic field at the center of a circular complete arc of current carrying wire carrying a current I and radius R. And then, of course, you can make a quarter of a loop be 1/4 of that, or a half a loop be 1/2 of that. And then, of course, you can also alter the radius, and you can also alter the current and all sorts of stuff. So anyways, keep that in mind, because that's a real nice way for us instructors to say, yes, my students were able to do the law of use of art, when you really don't have to do much hard work in doing it. You have to do some hard work to understand how you get it, And hopefully you guys got that from the presentations I gave you. All right, so I'm going to go ahead and share my iPad document. Make sure I've got the right one up. Yes, it looks like I've got 242-0302 because today is the 2nd. So yes, that's good. So I'm going to screen share my iPad. And this is going to allow me to choose this one, and it worked. So, all right. So what I want to do with you guys today is I want you to consider a solenoid. So what is a solenoid? Well, a solenoid is like what you used to call just an electromagnet when you were in grade school. So for instance, you knew in grade school, you could take a nail and wrap a wire around it really smooth, like, well, at least OCD people like me, who even then I knew I was a little weird and that I liked everything to be just right. But anyways, we would wrap it very smoothly around and then, you know, connect it to a battery. And then all of a sudden the current going through there somehow magically made a electromagnet. Well, that thing, whether there's a nail in it or not, is really a part of the circuit called a solenoid. And in fact, it's ultimately has a certain inductance associated with it. That's what we'll ultimately calculate. But right now we need to be able to calculate the magnetic field that's created by it. So just imagine a bunch of wires forming basically a helix, like a spring. A slinky. In fact, if you had housing to keep current from jumping laterally, you know, through the surface of the slinky from one surface to the next, of one layer to the next, that sort of thing. If you had housing around it to prevent that, then that would act just like a solenoid, as long as you had current going through it. So what I'm going to do is I'm going to draw a solenoid, and I'm going to do so by drawing a series of circles. And basically these circles are going to represent, let's say, current coming out of the page. And then these circles down here are going to represent current going into the page. Okay, the way we indicate that is really we just put a dot here, and that's like you're looking at the front of an arrow. And I mean like an arrow, like a bow and arrow situation. And this looks like you're looking at, say, the feathers in the back of an arrow. So that's how we indicate that. And in fact, what I can do, because of the greatness of modern technology, I can copy that and then I can paste it in principle. I know I can paste somehow or other. It's magic. I wanted to show you magic, but it looks like I can't do magic because I don't know how to paste. Oh, okay. Oh well. Anyways, I was going to put a bunch more, but I've given up on the task. I'm old. I can't do such things. So, anyways, what I'm going to do now.
So,
yes.
If you're using GoodNotes, you can just hold the pencil down, and then it should be able to paste.
Okay, yeah, that is what I'm using. So let's see. I was hoping someone would come to my rescue like that. So I'm holding the pencil down, and it looks like all that's happening is just pencils are coming up. Marks are coming up. This is
Okay.
really perfect.
Sorry.
That's okay. No, I'm happy to have someone try to give me some help. I was looking in the various settings and stuff. I don't know why it's not. It actually did the copy. Let's try again. So I'll do this. And I'll do copy, and I'll do this, and I'll do, it's got copy, cut, resize color. It's got everything but paste. I said but paste. Let's see if it's got paste in this other thing. Nope, no paste in there. Let's see. Nope, I don't even like that. Nope. Okay, let's see now. There it is. Yes, you were right. Thank you. Thank you very much. Okay, so now I've got a really impressive full-length solenoid. Check that out, with half the work and only 20 minutes of delay. Okay. What I'm going to do is focus on two of those top just for a second to show you something. So I'm going to zoom in on two of these top circles for just a split second. And what we will see Well, I should probably not draw with the lasso. That's not what they intended. Okay, so I'm going to draw two circles like such. Okay, and clearly those circles are not the same size, but I guess that's cool with me. Okay. And now I'm going to try to move. Whoa. Now you're getting smart. Okay. What I was trying to do was actually move it like this. And let's just get rid of that dot because that's just making me angry. Ooh, it's clear I do not know how to delete at this point. I'll just hold my pen on it. Nope, that didn't work. Okay, so the main thing I'm talking about here is as a result of this current that's coming out of the center of this, okay, and as a result of the current that's coming out of the center of this, each of these things are creating magnetic fields. And in fact, if you use the right hand rule, remember that means you can grab the wire with your right hand with your thumb pointing in the direction of the current. Well, in this case, the current's coming out of the page. So that's what I want to do. I'm going to imagine the current coming out of the page. So right here, as a result of this one on the left, I know that the magnetic field is pointing up. I also know that right here, the magnetic field is pointing to the left. I know that right here, the magnetic field is pointing down. And I know that right here, the magnetic field is pointing to the right. Okay. Now for the other one, I know that right here, the magnetic field is pointing down. And of course, by symmetry, they have to be equal in magnitude because they're both carrying current I. They're essentially the same sort of wires, that sort of thing. So one of the key things that you're getting from this, and this is part of the reason I'm blowing it up, is I wanted you to understand that at least between the two wires, the magnetic field is essentially zero. So down in this area, B is equal to zero, and that's just because they're canceling each other out. Now, that's just like right in between them. Now, down here inside of the solenoid, the magnetic field is strong. So B is strong down here because you can see that this left wire and the right wire are both contributing to the magnetic field. And in fact, if you have, 40 wires and you got 40 times the magnetic field adding, and they're just all contributing and making a really nice, almost, or well, essentially a uniform magnetic field going completely through the center like this. Now, just like when we dealt with this capacitor, it wasn't exactly uniform. We knew there was some fringe effects. So just like that, there are some fringe effects here. So as you get closer and closer to the edges, for instance, the magnetic field will start to deviate, but inside it's a fairly uniform magnetic field. And then, of course, up here above, outside, at least relative to inside the solenoid, the magnetic field is weak. So out here, I'm going to say B is weak. Again, that's at least relatively speaking. Oh, I should probably write that a little further apart so it doesn't just like I wrote the word biz. So B is weak out here. So we've got B equals 0 in the insides. We got B is strong in the solenoid, and we got B is weak on the outside of the solenoid. So that allows me to choose an Amperian loop. I'm going to apply, well, let's start off for this way. The actual question is, what is the magnetic field in the solenoid? So that's the real question I'm trying to calculate. Okay. Now, in fact, I'm actually calculating it everywhere, but I've got an idea here that just told me that basically, hey, the magnetic field on the outside is going to be obviously existing and obviously not zero, but it's not going to be anywhere near the strength of all of these things combining together. So what I'm going to use is I will solve it in green this time, and I'm not sure why I'm choosing green, but I did. Okay, what I am going to do is I am going to employ Ampere's law, which basically says the closed integral of B dot dl, and by that I mean the integral over a closed loop of wire, say, is equal to mu 0 times the enclosed current. And in fact, there's a rule that goes with that that basically tells us that when you go around this closed loop in a certain direction, if the direction around the loop is consistent with the direction of your right hand fingers curling, then the positive magnetic field would be consistent with the direction of your right thumb while those fingers are curling. If it's the other way, then you actually have to use a negative. So we got to keep that in mind as well. So what I'm going to do now is I'm going to create an Amperian loop. My Amperian loop is going to be red. And what I'm going to choose to do is I'm going to draw an Amperian loop that runs this way, like this, okay? And it's going to go there, there, there. Oh, not that one. One more out there, okay. Going to come up here, and it's going to be this way, that way, okay? So again, this is why I zoomed in to show you those spots so that you can realize that, yeah, there's going to be zero magnetic field right in between the two wires. The magnetic field that does exist from the bottom of the wire down to where the Amperian loop starts going parallel to the magnetic field lines, there the magnetic field's actually perpendicular to the line, so the B dot dl is going to give you 0. Similarly, most of the magnetic field on the outside, though it's really, really weak, so we might even just call it 0 from the get-go, but even the part that does exist is mostly going to be perpendicular to those sidelines, okay? Now, finally, that outer line, that top part of the Amperian loop, that one is actually going somewhat in the net direction of the magnetic field. But again, the magnetic field is so weak out there that essentially that B dot dl is equal to 0. So I'm going to write B is on the order of 0 out here. It does, however, point that way, so that's kind of helpful. B is essentially perpendicular to dl in this area, and B is perpendicular to dl in this area as well. So ultimately what we're going to get is obviously mostly nothing. In other words, the closed integral of B dot dl is mostly just going to be what happens with the bottom part of that line. Okay, so this was our Amperian loop. I'm just going to label that because I haven't yet. So just like before when we had Gaussian surfaces, here we have an Amperian loop. Okay, so now I'm going with my solution. I am going to make a hypothesis. Remember, we sort of use our symmetries and things that we learned about magnetic fields from just understanding how bar magnets and horseshoe magnets work, as well as using the law of Biot-Savart and seeing, how actual magnetism works. Because of that, we can make a hypothesis about what we suspect the magnetic field is going to behave like. So if I imagine a coordinate system, let's say a coordinate system like this, where that's my x-axis and that's my y-axis, then my hypothesis is going to be that my magnetic field is going to depend only on y, and it's going to point in the I hat direction inside. And I mean that inside the solenoid, of course. I've already made statements about what the magnetic field will do around the other two sides, around the left side, the right side, and the top side, essentially I'm going to get 0. So now I can write out left-hand side, and that is the closed integral of b dotted with dl is equal to the integral of b of y I hat. And now, at least for this bottom part, so I'm going to write bottom down here, or just BOT for bottom. In this bottom part, you can see that my little differential line element, which I'll draw as blue, that DL is actually DX I hat. Okay. I should probably put that back in green since I'm working on the solution. Plus an integral on the right-hand side, which I'll just say RIGHT here, is going to be essentially B of Y I hat dotted with, in this case, it's going to be positive DY J hat plus the integral of approximately 0 dotted with, in this case, negative dx I hat, and that's for the top, and then plus the integral over the left. So I'm showing you all the steps here, even though I want to just write down the very first term and leave the rest to be 0. In this case, again, it's going to be B of Y I hat dotted with, in this case, negative dy j hat. And of course, what you see here is when you have a essentially 0 for the magnetic field strength, that's going to be 0. Of course, when you have I hat dot j hat, that of course is also 0. And when you have I hat dot j hat here, that is 0 again. So I will say that our left-hand side is ultimately going to be, I'll put it right here instead of where I was writing it before. Our left-hand side is ultimately going to be just the integral of B of Y dx I hat dot I hat, which of course is just 1. And I'm going to integrate it essentially from x to x plus, let's say, L, because I'm going to assume that this length right here is L. Okay. So ultimately that just gives me B of Y times L. So that's the rule again. As I told you guys, I'm showing you all the gory details of what happens with the left-hand side of Ampere's law, but at the end of it, you should get like a magnetic field times a length, period. Okay. It might be 1 or 2 or 3 or 4 magnetic fields times lengths, plus 0, plus 0, plus 0, and all sorts of stuff like that. But at the end, it should be some kind of magnetic field times a length. You've seen, for instance, a case where it was 2 pi r times a magnetic field. That's a very normal thing. So in this case, we got 0 plus 0 plus 0 plus B of Y times L. Now, I'm going to assume that basically the solenoid has, let's turn it back to black, N turns, and L equals the length. So that means I can define something called lowercase n, which will be big N divided by L. Yeah, go ahead, Michael.
Could you, I don't know if you already said this, but why is it B of Y?
Because I made the argument, notice that I drew the y-axis up and down. it looked to me like if there was any possibility whatsoever to make B stronger, it would probably be the strongest right down the center and then maybe weaken a little bit as you moved up or down. So the only variable that made any sense that could affect the magnitude of B to me was Y. So I just put B of Y.
Okay.
Ultimately, what you'll see is it turns out that it's not dependent on Y at all. Does that make sense, Michael?
Yeah.
Okay. All right. Now let's do the right-hand side. So, and I probably want to go back to green. So right-hand side is mu 0 I enclosed. Well, we know the current carrying wire is carrying, even though I said it, I didn't state it, by the way, so I probably should have done that too. This is a current I. Okay. Well, through that Amperian loop, the actual current carrying wire goes through many times. So it's not really that reasonable to say that it's just mu 0 times I. It's going to in fact be something quite a bit different. So I'm going to move all this and put it down a little further just because it ran out of space really quickly. So I'm going to say right-hand side is equal to mu 0 times I enclosed. What we see is in fact a number of wires coming through there. So the total current should be the number of wires times the current I. Well, what that tells me is, since I can say lowercase n is what I'm going to define to be n divided by L, and I think that should be a constant, meaning we were, a little bit obsessive compulsive about wrapping the solenoid, then we should have the same number of wires in every inch that we have in the other inch. And in fact, we should have half as many in a half an inch, and in fact 4 times as many in 4 inches. So with that in mind, what I'm going to do is say, hey, I know that the length of my Amperian loop was lowercase l. So if I multiply that by the little n I just defined, then that should be the number of turns that I have. And then if I multiply that by the current, that should be the total amount of current going through it. So that's what I'm going to do. I'm going to say mu 0 n times L times I is the right-hand side. Now I'm going to say left-hand side equals right-hand side. Again, this is just like Gauss's law, in that you're not solving one side and working out to the other. You're actually solving both sides and then solving for something that's one of them. That's why I do left-hand side, right-hand side stuff. So in this case, I'm going to get B of Y. This is where you see that there is no Y dependence, is equal to mu 0 n times L times I, where lowercase n, of course, is understood to be the number of turns per unit length. You can see, in fact, that the L's cancel out, and ultimately what you find is the magnetic field within the solenoid. Whoa, it just all of a sudden switched to red on me. The magnetic field within the solenoid is actually equal to mu 0 times lowercase n times I, and it points, of course, in the I hat direction. And I left a little space to say inside the solenoid. Okay, does that make sense to everyone?
Yeah.
So that should be that should be a fairly straightforward calculation. Of course, I think your book does label mu 0 n times I with a number on it. So that means, like, on your final exam, that can be one of the equations you have on your equation sheet. It's no big deal. However, I do expect you guys to be able to derive these things as well. So I'm going to go ahead and do a toroid next. And then with the toroid, I'm going to go to a more advanced Ampere's law problem. that I think is worthwhile learning. So let's get started on that. Anybody have any last minute questions before I leave this example? All right. So what I'm going to do now is I'm going to draw that same solenoid, but imagine taking a solenoid that's really, really long and bending it until the two ends come together and it basically forms the shape of a donut. That's what a toroid is. So I would like to know what is the magnetic field within a toroid of radius r when carrying my brother is calling. Let me tell him. Okay. A radius r when carrying a current I through its in turns. Okay. So that's my way of like giving all the details. So I just went ahead and said, okay, it's carrying a current I. It has a radius r. I'll explain what that means with a diagram and so on and so forth. Now, what I intend to do is again draw a series of circles. Okay, and these are all the inner circles of the solenoid. And what I'm going to do is assume those are all the ends of the wires that the current's coming out of the page on. Like such. So they each get a little dot in the middle. And now I want to draw something like this. I'm curious to see if this is going to allow me to do it, but I'm going to try to copy it and see if I can make it bigger. We'll find out in a second if I can. If I can make it bigger, then I can just put it on top of this one and I'll have the same thing. I should have did it before I actually drew that, but so well. Here we go. All right. So now, whoop. So I'm going to copy. Oh, looks like I can resize too. Paste. And now I'm going to make it bigger. Who's you, daddy? Okay. That's a little bigger than I needed. Okay, that doesn't look too terribly bad. All right, so that's done. And in fact, now what we're going to do is we're going to say that these are all X's, of course. All my X's are on this circle. So you have a good country western singer too. All right. So this is the actual torus, or toroid, T-O-R-O-I-D. And now I've even managed to draw all the wires and everything. Wow, this is really a big deal. What I mean when I say radius R is I'm going to say basically that this is a radius R and that the distance from here to here we'll call A is way, way, way smaller than R, even though it doesn't look it. Okay. Now, if we use our right hand rule with any one of these inner circles or outer circles, I think what you'll realize is that this is going to create a magnetic field that goes around this way in the, of course, clockwise direction. Okay, so that's the magnetic field. I am going to Let's imagine a coordinate system. Let's say this is my x-axis and this is my y-axis, like that. And from that, I am going to work out my solution. This time, I think I will do my solution in, I think I'm going to do it in a pretty blue. Okay. So solution, what I'm going to use is the integral of b dot dl is equal to mu 0 I enclosed, i.e. I'm using Ampere's law. My hypothesis for this magnetic field is, in fact, notice this is why I drew the coordinate system like I did. It appears to me the magnetic field points in the theta hat direction. Remember, if we imagine this as, let me put another color in here. Let's say I'll do this green. If I imagine this is the r hat vector, because it points in the direction of the increasing variable r from polar coordinates, then 90 degrees ahead of it is the unit vector theta hat. So obviously if unit vectors are that big, then I'm pretending the solenoid's really teeny, but the main thing is I just wanted you to have an idea what I was talking about. And you can see whenever this angle theta changes, because r hat really is a function of theta, you see that the r is going to change, and the theta in fact goes in front of it too. So we can see that theta hat is actually theta as a function of theta itself. Okay, so my hypothesis is, as I told you, that the magnetic field may in fact depend on only one variable, r. So I'll write it as b of r, and it will in fact point in the theta hat direction. And I'm going to say that my dl is going to be, one of my students was asking about this the other day. He's one of my pretty strong students, so I'm assuming you guys might be having the same issue. So what I'm going to do is I'm going to switch colors real quick, and let's use this little dark green here. So what I want you to imagine is maybe I allow this theta to go all the way to here. Okay. And then I allow theta to go a little bit further, or I just erase it because that's what this program wants me to do. Oh, and it did it again. That was helpful. So helpful. Okay. So I'm going to allow it to go a little bit further, even though it looks a lot bigger than a little bit. That little bit is in fact d theta. Okay. Now, from trigonometry, we learned, this is one of the first things we learned when we started talking about radians in trigonometry, is that if you have a circle of radius r, and you allow that radius to sweep out an angle theta, then the arc length along that circle S is equal to r times theta. So the arc length along this circle is in fact r d theta. Because as I said, r points basically to where that magnetic field line is, and basically the inner string of wires and the outer string of wires are very, very close to each other. So you don't have to, dicker too much with regards to how much r varies from one side to the next. So I'm going to say, in fact, making my Amperian loop a radius r. Oops, I should probably stick to my blue color. D theta. That will actually be my DL. So this little vector right here is RDL. And actually I should write it in red because I'm trying to make this my Amperian loop as well. So I'll say right here, there's my DL vector. Actually, let's get rid of that. I want that back. Okay. This is DL. And in fact, my Amperian loop goes the same direction as the current does. And is essentially the same direct, or excuse me, as the magnetic field does. And my Amperian loop is essentially the same as the magnetic field line. So there's my Amperian loop. So now I can go ahead and start off with my left-hand side. So the left-hand side, the integral, closed integral of B dot DL is in fact equal to the integral of B of R theta hat dotted with R d theta theta hat, which and actually I should really, well, now that I'm doing a line integral, I have to make the argument of this integral, I have to make it be on the actual path. Well, as I showed you, the path is actually a circle of radius r. So the B is going to become B of capital R. So I'll write B of capital R. The R is in fact a constant that comes out in front. And then I get the integral of d theta times theta hat dot theta hat, which theta hat dot theta hat, of course, is 1. And this is going to be integrated from theta equals 0 to 2 pi. So finally, I get 2 pi r times B of R. Any questions on that? Now I can do the right-hand side since it appears no questions. Okay, so the right-hand side is just mu 0 I enclosed. Notice that if I put my right fingers down in the direction that the DL, or excuse me, that the path is oriented, then my fingers are pointing this way, and all the currents inside point out of the page, which is the same direction as my right thumb is pointing. So all those currents are in fact positive. And the problem told us that there were in fact N loops of wire. So all I have to write for this side is just mu 0 capital N times I. So now I can write left-hand side equals right-hand side. And that's going to give me 2 pi r B of R is equal to mu 0 N I. RB is actually going to be equal to N times mu 0 I over 2 pi R, all of that in the theta hat direction. And this is inside the toroid. And that's it.
Why is there no L for the right-hand side?
Okay, there did turn out to be an L for the left-hand side, and of course that's 2 pi R. But the right-hand side only has to count the total amount of current. And I said that the toroid was made of basically N, capital N, loops of wire. So the total amount of current that's coming out of the page inside of that Amperian loop is capital N times I. That's it. If I used a lowercase n, which would be the number of turns per unit length, then I need a length as well.
Oh, okay.
Does that make sense?
Yeah.
All right. So That was a Ampere's law problem that is, sort of the last of the quote unquote simple ones, I believe. Notice it actually is the same thing as the current you get from an infinitely long wire if you were a distance r away from it. Okay. But it's that multiplied by the number of turns of wire. Because remember, for a long straight wire, it was just mu 0 I over 2 pi r. So it's the same formula. Additionally, the book, I think, labels this one. So this is another equation you can have on your equation sheet if it is numbered. So keep that in mind. A lot of the times they're just asking you to apply this. They're not asking you to derive it every time. When I went through this course, I derived it every time, but I'm an idiot. So I don't think I was supposed to do that. And it made it for my test taking a long time, even though I've made good grades. I took it longer than everybody else. So I suspect a lot of times when I was doing derivations, I wasn't supposed to be. But that being said, derivations are ultimately part of it, because that's why they make up other problems that have slight changes. So let me show you another slight change that I'm going to do for Ampere's law. So what I'm going to do right now is I'm going to imagine the x-axis pointing up. So I'm going to grab my black colored pen and I'm going to set this up so that it does it nice and neatly. Okay. So that's my x-axis pointing upward. Oh, I should probably do that part a little later. Now my y-axis is going to be coming out of the page like so, and into the page like so. Okay. And then my z-axis is going to be going this way and this way. Okay. So now, as I said, this is my x-axis, this is my y-axis, and of course this over here is my z-axis, and I'm going to draw a very specific shape. What I have is an infinitely long, basically a coaxial cable. So what I'm going to do is I'm choosing a color now. I'm going to go with a green coaxial cable. And what I'm going to do is assume that the coaxial cable in cross section looks like this. Okay. And in fact, it goes for infinity to the left and to the right. In fact, let's see if I can take this thing away. Oops, guess not. I like making use of the straight lines. And of course, that's going to go on to the left too, even though I just drew it to the right. So now I'm going to draw it this way. And I'm going to draw it this way. Okay. Oops. That's not very good. That last one wasn't. Okay. So that's me looking not only at the wire, but looking at the cross section of the wire. And in fact, this part over here, I could actually draw like this, and that way we could see both ends. Okay. But this end over here, again, it goes on forever. Again, it goes on forever. Okay. And what I'm going to have over here is a current. I did not mean to do that color. I tried to do it in red. Is a current going this way whose amount is I. Okay. Now outside of this, by the way, the radius of this is B. So I'm going to say this radius right here. No, I'm going to say it's A. I don't even know why I said B, but it's A. Okay. Now I'm going to draw the other part of the wire. Which looks like this. Okay, and that's just the inner part. It's like the inside of a cylindrical shell, if you will. And that cylindrical shell has a radius B. Okay. Now, it also has, of course, an outer part. Here's where I'm going to go ahead and draw this. Let's see, this is a circle. That now I have an outer part as well. And it's right here. And an outer part as well. It's right here. Oh, dang it. I hate that thing when it thinks it knows what I want to do. Ugh. Okay. And over here, we get to see all the gory details. So this is going to be kind of close over here, but kind of far down here because of perspective. And this is going to be kind of close over here, but kind of far down here because of perspective. Well, it shouldn't be that bad. That last one was just a horrible thing I did. Okay, that's good enough, I guess. All right, again, all this stuff goes on for infinity. And in fact, the very last radius that I'm drawing here is in fact C. And lo and behold, guess what happens here? Well, there's a current, a total current I going this way in this one. Okay. And this is a anomalous thing in nature, but the current is uniformly distributed throughout. What that means is basically, let's see, I'll draw it in blue so it'll stand out a little bit. I think I'll draw it in blue. It won't let me take blue. What I mean by that is the current density J is a constant, and it's in fact going to be I over pi a squared. But that's also going to be equal to I over pi c squared minus b squared. Okay, so that's what I mean by the current's going to be uniformly distributed throughout. And that is an oddity in nature that doesn't necessarily happen. In fact, what we normally get, and Oliver Heaviside wrote quite a bit about this, was that the current was in fact going mostly on the outside edges of the wire instead of through anything. And in fact, if you look at Veritasium, which is a really good YouTube channel, I highly recommend you guys paying attention to it. If you want to learn some really interesting physics and engineering type stuff, Veritasium is a good one, and it's actually, you know, science as opposed to pseudoscience, so that's kind of helpful. But anyways, check out Veritasium. They actually handle some real stuff on there, and anyways, it's just really good. But in that case, they actually have where they show you that in fact the energy of the whole current carrying wire system is actually not even going through the wire. It's basically all tied up in the electric and magnetic field that's established around the wire, essentially. So that's kind of neat. And I don't know why I'm obsessing about these little lines here. I probably shouldn't be doing it, but I can't not do it now. It's so terrible. Make it bigger, bigger. Close enough. Okay, that's good. All right, I really just like that line. Now let's see if I can do this one a little better. It's just too big. I always end up regrouping my stuff. Oh well, I'll leave it be. So what we're going to do is find the magnetic field everywhere. So my problem here is B equals question mark everywhere. Okay. So first off, I'm going to start with, let's do the solution in blue this time. I'm going to first I'll start with R less than A. And what I mean by that is I am going to draw an Amperian loop whose radius is R, but is in fact smaller than A. Okay. And now, in addition to that R being there, I am going to choose that I integrate around it so that the front is the current, or I'm integrating downward in front of that z-axis, and in fact integrating upward back there behind the z-axis. And we can in principle show that by switching this to black, and then maybe doing a little, if I can get it even bigger than that, maybe doing a little of this, just to sort of indicate that I'm going back behind something, and therefore you shouldn't be able to see it completely. Okay. So I'm going to make my normal hypothesis, of course, and now I think you guys are advanced enough where I don't have to take the time and write what the hypothesis is. I suspect you even know specifically why I chose my X and Y axis that way, because I'd have a very specific direction for the magnetic field. Does anybody want to guess what my hypothesis is for the magnetic field? How about for the direction of the magnetic field? Nobody?
Is it in the K hat or the R hat?
Close. Remember, we were talking about, well, imagine this. Let's forget about the complexity of it here. Let me see if I can talk you through this a little better. Let's imagine here, instead of this complex system we're looking at, think for a second that we're not really looking at all this different thing. We're just looking at that inner wire. So you've got a wire who's going from left to right, and whose current is actually going to the right. What direction would the magnetic field point above that wire? Would it point out of the page, in the page, to the right, to the left, up, or down?
Wouldn't it curl around the wire?
Yes, it would curl around the wire. That's exactly it. So when you wrap your hands around the z-axis, your thumb pointing in the positive z direction, I think you realize that it's coming out of the page at the top, right?
Yeah.
So you think it's going here at the top, and I suspect you think it would be going in the page down here. Would you agree that it's also going down out in front? Does that sound right, Michael? That the magnetic field?
Yeah.
Okay, and it would be pointing up in the back. Do y'all recognize that as the actual theta hat direction?
Oh, it's 90 degrees to R hat.
Exactly. So I'm going to say my hypothesis, which is going to be this over and over again, is likely the magnetic field's only going to depend on how far away I am, but it's going to point in the theta hat direction. And in fact, the DL is going to consistently be R d theta, theta hat as well. So I will just do that over and over and over again. So now I can say left-hand side, closed integral of B dot DL is equal to the integral of B of R theta hat dot R d theta theta hat, which turns out to be just 2 pi R B of R. The right-hand side is a little more complicated because we have to make use of the fact that the current, when we're doing R less than A, the current enclosed is not completely I. So what I'm going to do is I'm going to go ahead and write I enclosed divided by the area of the Amperian loop that's actually enclosed by the Amperian loop. So that'd be pi R squared. And I'm setting that equal to J, which is I over pi A squared. So I can see now that the right-hand side, which is mu 0 I enclosed, is in fact going to be equal to mu 0 A squared over, excuse me, mu 0 R squared over A squared times I. Now I can set left-hand side equal to right-hand side. And when I do that, I get 2 pi R B of R is equal to mu 0 R squared over A squared I. You can see that the exponent of 2 cancels out with one of the R's over here, leaving just a single R on the right. So now I can finally say that B is equal to mu 0 I over 2 pi A squared times R, but it points in the theta hat direction. And this is for R less than A. Okay, now I do the next part, which is A is less than R is less than B. So my hypothesis and all that stuff's going to be the same, but luckily in this case, the current enclosed by the Amperian loop, does everybody recognize what the current should be once I have the Amperian loop be completely out here? What current is enclosed in that new second Amperian loop that I drew?
I.
Exactly. Whereas that last one, it was a part of it. So this one should be easy peasy. I'm going to go ahead and say left-hand side, closed integral A dot, excuse me, B dot DL. It's just 2 pi R B of R. And I'm going to say right-hand side, mu 0 I enclosed is just mu 0 I. So I finally get that B is equal to mu 0 I over 2 pi R theta hat, and that is for A less than R less than B. And I think you can see if you actually plug in A equal to R, you'll see it's now okay to put it equals to in that symbol as well, because it is in fact continuous. All right. Now the next part is I've got to do B. Whoa, I should probably write that in blue. Next part is I've got to do B is less than R is less than C. So my Amperian loop in this case is going to be up here somewhere. And in fact, we're going to call that R. And this is for, again, B less than R less than C for that Amperian loop. But again, we're still going in the same direction and everything. So for this one, we have, as you might suspect, the same hypothesis. So the left-hand side is going to turn out to be the closed integral of B dot dl, which is equal to 2 pi r B of R. I enclosed, however, is going to be a little different. Anybody have any ideas how we're going to treat I enclosed?
I have a question
Yes.
for the thing with the radius B. Is that one carrying a current?
No, well, yes, it depends on what you're saying here. So the radius B is the inside edge of a cylindrical shell.
Oh, okay.
Okay, so the current is being carried through that shell. And this is exactly like coaxial cable that's used for DirecTV, Dish Network, and cable television. Except when you look at, if you opened up coaxial cable that they use for television, you'd see a single little copper wire in the middle. And then on the outside, you'd actually see braided aluminum wire just inside of the housing. That's the actual wire on the outside. It's just a thin little aluminum shell of braided wire. But yes. Okay, so remember now with this new Amperian loop, I don't just have the current for the shell, I still have the total current that's going to the right. So I wrote I enclosed as I minus something, okay? And the reason I'm saying it's minus is notice I'm still integrating in that same direction, which is down in front of the wire. Below the wire, it's in, behind the wire, it's up, and above the wire, it's out of the page. Well, that's exactly in the opposite orientation for the current direction. The current's going in the opposite direction that my right thumb points when I put my fingers in that way. So that's why I put the minus there. And in fact, I have to use the fact that the current is uniformly distributed to reach the conclusion that I part, which I'll just say I sub P over pi R squared minus B squared, because that's how much area. Whoa. I'm going to write it here bigger. That'll help me. So in this case, I'm going to say the part that I'm going to be subtracting is IP, and that's over pi R squared minus B squared, because obviously there's no current flowing for R less than B, but that has to be equal to I over pi C squared minus B squared, because that is the constant uniform current density J. So what I'm saying is this quantity right here is what we labeled IP. So now I can say that the right-hand side of Ampere's law, which is mu 0 times I enclosed, is equal to mu 0 times I minus mu zero. Now we're going to get r squared minus b squared over c squared minus b squared times I. So that's a holy mess, but anyways, that's what it is. So now I got to go to the other page because, good, we got 10 minutes left. I got to go to the next page and say left-hand side equals right-hand side.
So
Stuff
could you
just
go back for a second?
was, yes, I can.
All right, thank you.
Pretty tough, ain't it? So I've got now 2 pi r b of r is equal to, and it's really hard to figure out how you want to write this, but you could write it as mu 0 I minus r squared minus b squared over c squared minus b squared times I, if you wanted. That gives me that the magnetic field, at least where we're talking about, is mu 0 I over 2 pi r. And what I'm going to do now is I'm going to have assumed I just factored out the I from both sides. And then all I have left is 1 minus r squared minus b squared over c squared minus b squared. You could actually take the time to get a common denominator here and get something nice and maybe even pretty in there. I'm not sure, but anyways, and this is for, of course, b less than r is less than c. And if you look back and consider r equaling b, notice if r equals b, the numerator of that fraction becomes 0, and you just get mu 0 I over 2 pi r, which is in fact b. That's exactly the same thing that we got for the one for a less than or equal to r is less than b. So now I can put a equal symbol there and an equal symbol there as well. So that's our magnetic field as we eke closer and closer to R equals C. All right, so we got one more part. We've got we've got C is less than R is all we have left. Now, if we go back here and look, we can make our Amperian loop. Our Amperian loop is going to look something like this. Okay. And again, its radius is going to be R, but in this case, it's C less than R. Now, does anybody have any idea or any grand predictions you want to make about this? Again, we're going to be integrating downward in the front, upward in the back, and outward on top. But do y'all see any really nice simplifications or anything that make this last part easy?
It's going to be negative, right?
The whole contribution from the shell is absolutely going to be negative. Do you know what the total current will be though once you get to any R greater than C?
Zero.
Yep. And what do you think happens when the current is 0?
Is the magnetic field 0?
Yep, that's what's going to happen. So yeah, that's the grandiose conclusion I want you to make. And it's not unlike this one. if you remember when we did Gauss's law, you could have a charge, for instance, positive Q, say on a sphere, uniformly distributed throughout a sphere, whatever, it doesn't really matter, to be honest with you. And then you could have yet another sphere outside of that one. And that sphere, in fact, could have a charge of negative Q. And then once you make your Gaussian surface, which, whoa, I did not mean to do that. Didn't mean to do that either. Which is a sphere of radius bigger than these things. You can sort of see it here. Then the closed integral of E dot dA, which is equal to Q enclosed over epsilon naught, is actually going to be equal to 0 because Q enclosed is 0. So that means E outside equals 0. And that's the same thing that's going to happen here. So now we're going to work it out. We're going to say, okay, left-hand side, closed integral B dot dl is in fact equal to the integral of B of R theta hat again, dotted with R d theta, theta hat again, which is equal to 2 pi R times B of R. Now the right-hand side, which equals mu 0 I enclosed, is equal to mu 0 times I from the inner one, and then minus I from the outer one, which gives me 0. So I've got left-hand side equals right-hand side gives me 2 pi R B of R is equal to 0. So B equals 0 for R greater than R equal to C. And that's it. We've completed the world's scariest Ampere's law problem. It's not really the world's scariest. I actually thought of doing this instead of having it the current uniformly distributed. I was going to make the current the J, the current density, I was going to make that some constant times R. And that would have been even worse. But anyways, luckily I came to my senses and decided not to do it. So that's a pretty robust, actually, that's a very robust example of application of Ampere's law. So this is not one you normally find, for instance, in a book, except for maybe as an exercise as opposed to an example. So hopefully that'll help you better understand how to apply Ampere's law and so on. So does anybody have any questions about any of this process? It's obviously pretty big because it took 2 pages to do it. All right, well, class is supposed to be over now, or actually over at 6:40. I don't know why my alarm didn't go off. But anyways, we're going to go into chapter 29 next. I will tell you what I would suggest you start thinking about is imagine, for instance, a loop of wire like this. Actually, let's erase that and see if this thing can make it better. Yes, it can. Okay. Now, what I want you to do is imagine that all of a sudden I teleport a current carrying wire right here, meaning there wasn't one a second ago, but now all of a sudden there is a current carrying wire. And in fact, the current is pointing downward like that. Okay, so basically what we're looking at is, for instance, a lightning strike. All of a sudden, a lightning struck and carried a current downward. So we're pretending like positive particles have been taken down from a cloud above and are shooting straight down next to my loop of wire. What I'd like you to imagine is, once you read, say, the opening section or two of chapter 29, I would like you to say, in which direction is current induced? Because what's going to happen is, oops, I wrote an S there. What's going to happen is there was no magnetic flux through that loop of wire until lightning came. And then all of a sudden there was. And Faraday's / Lenz's law says that whenever you have a changing flux, an induced current will be created in such a way to oppose the change in flux. It opposes the change in the flux, not the flux. So in which direction will an induced current flow? So that's something you can think about. Hopefully you can figure it out on your own. If you don't, that's okay. That's why I'm, paid the big bucks. That's why I get, $1.5 million every year to teach you guys. Yeah, I make $1.5 million. Anyways, anybody have any questions? Of course, you're free to go. The class was over to 2 minutes ago. I will wait here until the last person has had any questions answered that they need answered. I have created the practice test, and I will be sending an announcement out within the next 30-45 minutes to let you know the practice test is up, and to let you know other details about that. That'll be practice midterm, practice test 3, practice test 4 as well, since I had forgotten test 3. So again, I apologize for that, folks. Y'all have a great spring break. Remember, no classes next week, the 5th through the 12th, we're off. You come back on the 13th, and our exam is scheduled for meeting this period for ideally an extra 25 minutes, so an hour and 45 instead of the normal hour and 20. So anyone have any questions? I gotta say, this is some of the prettiest notes I've ever done. All these cool pictures. I'm very excited about it. They will be up on my Google Docs page very soon. So
Sir, I have a weird thing with my grade.
yes. You want me to stop recording since we're talking about a grade thing here?
Sure, yeah.
Okay, hold on just a second. I am going to stop sharing screen. And now I'm going to